Okay, here's some more problems from section 9.5, and we've got some geometric series, and these are pretty easy because we don't have to worry about the endpoints because their interval of convergence is pretty much dictated by what we talked about in geometric series. So if we look at this first one, number 35, summation n equals 0 to infinity of x to the n, that would start out with x, then I'm sorry, with 1, then x to the first, then x squared. Then it's a geometric series where r equals x, and that converges only for the absolute value of r is less than 1, which actually means the absolute value of x is less than 1, and that's in this range here. That means x is between -1 and +1. So this is the interval of convergence, the IOC, interval of convergence. Open, -1 to 1 open. Converges absolutely. If we take the absolute value of this, we're going to get the same thing. There's no difference because there are no alternating signs or no negative signs, so it converges absolutely. And there are no values of conditional convergence. In other words, there aren't any points in here that don't converge absolutely, but that do converge because it converges absolutely over the whole interval. And you can just check that. I mean, the absolute value of that is just the same thing, so there's no difference. Okay, number 36. Okay, this is also a geometric series. Okay, and r is equal to, the ratio is x plus 5, because we keep raising it to the nth power, so we just keep multiplying by another factor of x plus 5. And that converges only for the absolute value of that ratio less than 1, or -1 less than x plus 5 less than 1. And then if I subtract 5 from both sides, I get -4 and -6. So this is my interval of convergence. Again, I can take the absolute value of this. It's going to be the same, so it converges absolutely. So there are no values that are a conditional convergence. All the values are absolute. Okay? And then number 37. So this is a little bit more to this one. There we go. So we have this series, -1 to the n, 4x plus 1 to the n. So I can rewrite this as -1 times 4x plus 1 all to the n, and I can see I have a geometric series, and this is my ratio. -1, 4x plus 1 times 4x plus 1, which converges only for the absolute value of that to be less than 1. And the absolute value of that would get rid of the -1. I could break this up and say the absolute value of -1 times the absolute value of that if I wanted to. Break that up into two absolute values, and the absolute value of -1 is 1. So it's basically this. So it converges for 4x plus 1 less than 1. All right, which implies that -1 is less than 4x plus 1, which is less than 1. If I subtract 1 from both sides, I get -2 less than 4x less than 0. And if I divide by 4, I get -1/2 less than x less than 0. And that's my interval of convergence right there. Now, you could look at it and pretty much guess the absolute convergence, but I just checked it just for completeness. So I took the absolute value of this series, and which is going to get rid of this -1. So this is the absolute value of -1, so that's just going to make that 1. So it's going to make it this series. And again, it's also a geometric series. And the ratio, again, is 4x plus 1, which converges as above because this 4x plus 1 would be the same issue. We'd have the same interval, -1/2 x to 0. So this also is an interval of absolute convergence. It converges absolutely on this interval. That was easy enough to see. So again, these are the only places where it converges, and it converges absolutely for all of our possible values. So there are no values of conditional convergence. Okay? So that's 37. Okay, so these are all pretty straightforward. And now the next one, and this is probably the most significant problem by far, as far as what we're doing. And these are the ones we want to be aware of. The other ones kind of simplify nicely, but this one has got a little bit of more substance to it. Okay? So let's take a look at this one carefully. So this is the summation as n equals 1 to infinity of 3x minus 2 to the n over n. So we'll start with the ratio test to find the interval of convergence, because it is not, okay, a geometric series. If this was n to the n, we might be able to make it into a geometric series, but it's not. Okay, so we're going to start with the ratio test. So we're going to try absolute convergence first to see where it converges absolutely. And if that works, then we're in pretty good shape. So we'll use the ratio test. So that's going to be 3x minus 2 to the n plus 1 all over n plus 1 divided by a to the n, or I can invert and multiply and make that n over 3x minus 2 to the n. And I just use put the absolute value on the x parts because the n's are always positive. Then we can expand this out to 3x minus 2 to the n times 3x minus 2, and these are absolute values all over n plus 1, n and 3x minus 2 to the n, and those 3x minus 2's to the n's cancel. I can put the n with the n plus 1 in front, times 3x minus 2. And if I take the limit as n approaches infinity of this, this is just going to be 1. Okay, we know that by many ways. So that's just going to be 1 times this, which is this. So my limit equals the absolute value of 3x minus 2. Now that's my L. Now remember this, by the ratio test, this series will converge for all L less than 1. So it converges for the absolute value of 3x minus 2 less than 1. And I got an inequality I could set up and solve. So negative 1, 3x minus 2 less than 1. Add 2, so that's going to be 1 and 3. Then divide by 3, I got 1/3 less than x less than 1. So that's where it converges absolutely. So that's my interval of absolute convergence. Okay? Now the interval of convergence will be all the points where it converges, so we have to check the endpoints. So be careful that you follow this, because this terminology could be a little confusing, so make sure you kind of follow all this stuff here. Try to get this up so everything's in frame here. Okay, I think I got it. Okay, so that's absolute convergence. Now let's check the endpoints. So first of all, I'll take x equals 1/3. Now I'm going to take 1/3 and put that back in the original series. Now remember, the original series was a summation n equals 1 to infinity of 3 times x minus 2 to the n over n. So now I'm going to put 1/3 for the x. All right, sometimes this is a little hard to see where this comes from. Okay, so I'm putting this right in the original series, and I'll simplify it. 3 times 1/3 is 1. 1 minus 2 is negative 1 over n. So we have a good old alternating series. So we can take a look at this, and this alternating series satisfies all the criteria for the alternating series test, or the Leibniz test. U sub n would be 1 over n. It's greater than or equal to 0. It's decreasing, and the limit is 0. So this series converges by the alternating series test. So it converges. Now let's check for conditional convergence. So we'll see, well, does it converge absolutely? Okay, so we'll take the absolute value of this. If we take the absolute value, that's going to get rid of the negative part. So I got the summation 1 over n, and that diverges by the p-series test, p equals to 1. All right, so it doesn't converge absolutely, but it does converge. So what do we say? It converges conditionally, so it's conditional convergence at x equals 1/3. Okay? But it does converge. It's just conditional, but it does converge, so it would be part of the interval of convergence. Those are all the values for which the series converges. So it does converge. It just happens to be conditional convergence, not absolute convergence. Now let's check the other endpoint, x equals 1. So again, I'll put 1 in the original series. 3 times 1 minus 2 to the n over n. And then that's just going to be 1 to the n over n, which is just 1 over n. Now we know that this series diverges by the p-series test, p equals 1. Also, as over this other example. So therefore, it doesn't converge at all at x equals 1. So when I go back and have to answer the questions, A, they wanted the interval of convergence. The interval of convergence, let's see, I'll move this up just a little bit. I'm sure that's in frame, but just in case. So the interval of convergence was the 1/3 and inclusive, because it does converge there conditionally, but it does converge to 1. It doesn't converge at 1, but that's part of the general, the interval. Remember, we have this one. This is my absolute convergence, so absolutely I converge my convergence is in this range, okay? But it also converges here, so my interval of convergence is 1/3 closed 1. Where is it absolutely convergent? Just in this interval here. It's not absolutely convergent here at 1/3 because I checked over here and when I took the absolute value, it diverged. So it's conditionally convergent there at 1/3. So that answers C. Okay? Interval convergence, interval of absolute convergence. Okay, so since these aren't the same, this is going to be where it converges conditionally. This is where it converges, but not absolutely. So think about that. Make sure that makes sense to you, because that's probably the most important one. That's like the examples we've been doing the last couple of days. Okay, so I hope those help.